Your photocopy looks a little weird because it's missing these things. The learning goal is not all that useful. I just thought I'd fill something in. So we're going to do a whole bunch of things today with angles and standard position. So all these little tips and tricks, like you're a detective, you got to pull a bit of evidence from here, a bit of evidence from here, a bit of evidence from here. Cast is one of those things. You remember cast? What does cast tell us? It tells us where each of the ratios is positive. So they're all positive in the top right quadrant. That's what the all stands for. And then it's only sine, only tan, only cosine in the other three. And that's how we remember which quadrant each of those ratios, or its reciprocal ratio, we'll talk about those in a moment, where each of those is positive. Who's heard of our valiant knights or kicks or ticks? None of you. You've heard of them. Okay, yeah, you have. Okay, very good. But some of you have. Okay, and some of you maybe haven't. So Sir Kicks or Ticks is a really useful little thing. This is like the grade 11 version of SOHCAHTOA. So you know SOHCAHTOA. Everybody knows that. Sine is opposite over hypotenuse. But when we are dealing with angles in standard position, Sir Kicks or Ticks is easier to use. Okay, so it's the same concept though. Sine is y over r, which is the radial arm. Cosine is x over r, and tan is y over x. So if you haven't been introduced to Sir Kicks or Ticks, there you go. It's our version of SOHCAHTOA that works with angles in standard position. But what exactly does that mean? So we've got a few little diagrams here. The basic idea of angles in standard position, if you remember, is we have what's called a terminal arm. And it always starts there. So that's where we measure our zero from. And then from there, it rotates up into quadrant 1 and then starts rotating around. So it rotates, rotates, rotates. In fact, we can see that happening here. So here's our arm, and I rotate it around. Okay, and I can rotate it as many times as I want because it can keep going, keep going, keep going. And after I've gone one full revolution, that's 360 degrees. I could, if I kept going, it'd be more, like 361, 2, 3, right? So you could keep doing that. But no matter what, the arm always ends in one of the 4 quadrants. And then the standard, this is what we mean by angles in standard position, is that it creates an angle with the x-axis. So that's always the angle that we are talking about. So if I put it there, that looks like a 45-degree angle, okay? And you can see the blue and the green are the same. But if I come over here and put it at about 45, can I get about 45? There we go, about 45. So my related angle is 45. The related angle is always made with the x-axis. But then my actual angle is the green one. So it's like 90 and then more, right? 45 more, or 180 minus 45, right? So it should be actually 135, but whoops. We can't get it. Let's see if I can get it right on there, right? So this one should be, there we go, 135. So we have these angles that are related to each other. As the arm spins, it's creating some kind of big angle. So it's going to get bigger and bigger and bigger, and down here there's 219 degrees. But it's always got this acute related angle that's made with the x-axis, and it makes a right triangle. That's why SOHCAHTOA works, and this is why when we think about Sir Kicks or Ticks, this side length, okay, is equal to the y value at that point, because it's from x where it's 0, where y is 0, down to here is my y value. So I can see that it looks like it's about around 0.75 there, right? And so SOHCAHTOA would tell me that from this blue angle, opposite over hypotenuse, or y over r, is the sine ratio. That's Sir Kicks or Ticks, right? So it's the same idea, but it uses our coordinates as opposed to thinking about SOHCAHTOA, okay? So it all has to do, so all the skills that we learn when we talk about angles in standard position have to do with that relationship of the terminal arm going to some big angle, okay, but there's this related angle. And a part of the reason why we do this is when you punch in, like, if you want to find the angle that goes with 0.5 for sine, okay, so sine theta equals 0.5, it'll always give you the acute angle. It's not going to tell you what the angle in quadrant 3 is. But we want to be able to figure out all the angles. So that's where all that other little tricky stuff comes in, where you have to start problem solving, thinking what's positive, what's negative, that kind of thing. Okay, we'll do some examples and you'll see that. Okay, so for example, if what these pictures are about is if I have a small angle like that, you can see that the related angle in each quadrant is also nice and small, but my terminal angle would actually go all the way around like that, or for the red one, it always starts here and goes all the way around like that, and then obviously for the green one, it goes all the way around like that, but it has this small related angle still. And then if I make the angle bigger, then it's the same thing. All these angles are equal. The angle that it makes with the x-axis is always the same, but the angle around, you can see, is different. Whoops, doesn't matter. Okay. And if you remember, this is quadrant 1, quadrant 2, quadrant 3, quadrant 4, and so we need these tiny little formulas to remember how to find the related angle, or what's the relationship between the terminal angle and the related angle in each of these quadrants. So in quadrant 1, so we have theta related equals whatever, okay? So it could be a small angle like in the first picture on the left, or it could be a big angle, whatever it is, theta related is the one that's always made between the terminal arm and the x-axis, okay? So no matter what quadrant you're in, it's always an acute angle. So for quadrant 1, how do I find theta? Well, it's just equal to theta related. In quadrant 2, theta is going to be equal to 180 minus theta related. Okay, so if I got rid of all this, I would go around to 180 and then subtract to get back and figure out what's left. And then you can use these formulas in reverse if you have the actual angle and you're trying to find the related angle, obviously. Okay, so quadrant 3, theta is equal to 180 plus theta related. And in quadrant 4, theta is equal to 360 minus theta related. Knowing the values at each axis is important. So obviously this one's easy. It's 90 degrees, 180, 270, and then if you go all the way around, it's 360. So we kind of keep that as a frame of reference. So if somebody tells me that theta is 115, I automatically know what quadrant that's in. It's between 180 and 90, so that'd be in quadrant 2. If somebody tells me that theta is 290, then I know I'm in quadrant 4. It's bigger than 270, smaller than 360, right? So again, sort of pulling in pieces of information from all different areas to solve these problems, whatever the problem happens to be. Lots of different kinds of questions in this. So here's a little applet showing, if I drag this around, how you can see how theta related is each of these colors, and it's always the same, right, for each of them. And you can see how the y value is the same for each, but if I'm below the x-axis, these y values are negative. So that one's negative and that one's negative, hence the cast rule. That's where that comes from. These y values are positive. In these two quadrants, quadrants 2 and 3, the x values are negative. R, which is like the radius of the radial arm, is always positive because it's a length. It's always positive. Okay, so I can turn this on and I can show the actual angle to the red arm. And as I'm increasing my theta related in this case, I can see how that impacts theta, the actual terminal angle, right? So just thinking about the relationship between those, and then for each quadrant, it's a little bit different because it's 180 minus, 180 plus, or however it works out. Any questions about that so far? Oh my goodness, so there's so many different kinds of questions. So first of all, just very quickly, what is the angle in each quadrant if the related angle is 34 degrees? So that's what we just did. So let's get started. So how do we do this? Theta related equals 34 degrees. I think this is my own notation. I think I made this up, so don't expect other teachers necessarily to know this, but I really like it. You can tell me if you've seen it before. So I like to name the quadrant as like a subscript. So theta in quadrant 1 is equal to theta related, so it's 34 degrees. Theta in quadrant 2, and I use Roman numerals because that's what we usually use to name the quadrants, is equal to 180 minus theta related, which is 180 minus 34, which is 146. Very good. Theta in quadrant 3 is 180 plus theta related. So we don't go to 270. We always, like everything's from the x-axis, right? Remember that. Everything's to do with theta related is from the x-axis. So that's 180 plus 46, which is 226 degrees. Oh, 16. No. Oh, I wrote the wrong angle. Where did that come from? Oh, 46 from the last one. Thank you. Plus 34. So that's 114. 214. This is what happens when you try to rush. Okay. And then theta in quadrant 4. So again, starting at the x-axis, but going all the way around, right? So that's where we get the 360. So like little mini formulas. But as long as you understand them, you kind of recreate them. You don't necessarily have to. So 34, you don't have to memorize them, I don't think. 360 minus 34. Okay. So that's like usually just a part of a bigger question. And it's not usually that we're finding it in all quadrants. It might be just one quadrant, or it might just be two quadrants. Okay, different kind of question. Example number 2. Point P, negative 512, lies on the terminal arm of an angle in standard position. State each trigonometric ratio and each reciprocal ratio. Determine the related angle and the actual angle. I don't know if we'll have time for all that. We'll see. Okay, so first thing I'm going to do is sketch this. So negative 512. Oh, that is not right. Negative 512. So that is in quadrant 2. And my terminal arm goes all the way through it, or it stops at the point. Doesn't matter. Like, if you think about similar triangles, the arm can keep going, but we're going to worry about it, obviously, just to this point. So there's my triangle. There's my right angle. So that means that my y value is 12, so the length of that is 12. And the x value is negative 5, but the length is 5. So how do I find the length of the arm to that point? Say again, Chad? Pythagorean theorem, exactly. C squared equals A squared plus B squared. C or R is going to be the square root of 12 squared plus negative 5 squared, which works out to 13. Remember, it's always positive because it's a length. The y and the r come from coordinates. They can be positive and negative. R is a length. It's always positive. Never forget cast. Okay, so sine of theta is, sir, kicks or ticks, is y over r. So in this case, that's 12 over 13. This is how we state each of the ratios. Cosine theta is x over r. If I look at the diagram, this makes sense. There's my theta related that I'm talking about. So cosine is adjacent over hypotenuse. That's x over r. See how that works? Sine is opposite, which is the y value over hypotenuse, so over r. So this is, x is negative. Actually, let's write that out just to be clear. So x equals negative 5. This is how I do it in grade 11. I get them, like when we're doing these questions, I have them all write them all down in the same place like that. Okay, so I get negative 5 over 13. Tangent theta is y over r, opposite over adjacent. So that is, so y over x, did I say r? So that's negative 12 over 5. Positive 12 over negative 5, negative 12 over 5. What about the reciprocal ratios? Who remembers those? Brandon, can you name one of them? Secant. Which is, when does secant go with? Pardon? Oh. Cosine. It's switched. It's what, I don't know why they did. I'm sure there's some reason, like from the Latin or something. I should know this. But like there's sine and cosine and secant and cosecant, but they flip, right? So sine and cosecant go together, and cosine and secant go together. Okay, so sine and cosecant, that's how we call it, of theta, is just 1 over sine. So that's 13 over 12. Secant theta is 1 over cosine theta, which is negative 13 over 5. And then the last one is cotangent. See, that one makes sense. I don't know. 1 over tan, which is same sign, negative, and then 5 over 12. And determine the related angle and the actual angle. Okay, yeah, we can do this. Okay, so what's the related angle? I can use any one of those to figure it out. So I'm going to get my calculator out. This is how we do these kinds of questions. Oh, I should have this. And I would go, I'll use the first one. So shift, sine, bracket. Everybody's a little bit different. 12 divided by 13. So if sine theta, and this is theta related, by the way, equals 12 over 13, then theta related equals, oops, mine's in the wrong mode. We'll talk about that on Monday. Shift sine, bracket, 12 divided by 13 is approximately, we'll just do it to the nearest degree, so 67 degrees. Did everybody get that? Try it on your calculator, it's important. Remember, for this, your calculator has to be in degrees. There's these other modes that we will actually use in grade 12, but for now, for today, for this weekend, you're using degrees. So make sure you get the right answer. You have to put it in brackets, or if you have like a one-line calculator, you would do 12 divided by 13 equals, and then hit shift sign. Okay, or shift sign bracket 12 divided by 13, you should be able to get 67 degrees. But it's not, theta isn't 67 degrees. Theta is this, right? I know what quadrant we're in. So I use the quadrant 2 formula, which is 180 minus theta related, so 180 minus 67. So theta equals 180 minus theta related, which is 180 minus 67, which is it's important that when you do this step, you call it theta related. Even if it's in the first quadrant, you should still be calling it theta related because that's what you're doing. And then even if it's in the first quadrant and theta is theta related, you still make a separate statement to state what theta is, okay? So we always calculate theta related and then do an extra step to figure out what theta actually is. Make sense? Any questions? Oh my gosh, we only have 10 minutes left. Can we do all of special triangles and graphing trig functions in 10 minutes? I don't think so, but we'll do our best. Oh my gosh. Okay. Yeah, I'll finish the video and you can watch it later if you want. But so special triangles, very quickly, comes from this idea that there's a few angles that, let's say, come up more often in life or whatever. And so if I start with an equilateral triangle, then all of my angles are 60. So this is 60, and this is half of that. So that's 30, and this is obviously 90. So it adds up to 180 like it should. And what we start with is side lengths of 2. And so then this side length gets cut in half, and then I use Pythagorean theorem to find the other one, so square root of 3. And then this one is an isosceles triangle with 2 angles of 45 degrees, which means my other one is a 90-degree angle. Okay, and I start with side lengths of 1, 1, and root 2. Or you could also start, well, I don't think we really do this, but you can also, I mean, if you want to kind of memorize, you could have square root of 2, square root of 2, and then this one would be 2. So sort of 2, like those relationships both work in terms of Pythagorean theorem. So determine the possible values of theta if 0 is less than or equal to theta, which is less than or equal to 360 degrees. So remember, we always have this condition, because otherwise you would have an infinite number of answers, because the terminal arm could keep going around. So if one of my answers was 45, and I didn't put a restriction on like the domain that it can exist in, it'd be 45, and then 45 plus 360, and then 45 plus 540, and then 45 plus 720. Like all those would work, right? So we usually talk about between 0 and 360, but sometimes it's 0 and 180, or sometimes it's 180 and 360, or who knows, right? Okay, so what we want to do is we want to look at this relationship, which is 1 over root 2. So that means I'm dealing with the 45-degree angle kind of question, right? So theta related is 45 degrees, and it's positive. So cast tells me that it's in one of the top 2 quadrants. See how I'm using all bits of different information to solve these questions? So theta in quadrant 1 is equal to theta related, so that's just 45. And theta in quadrant 2 is 180 minus 45, which is 135. Okay, B, cosine theta is -1. What does that mean? It's always a ratio. Cosine is a ratio. Tangent is a ratio. Sine is a ratio, right? So circix or tix. This is where x over r is 1. So x and r are the same. Where does that happen? Right here, when it's negative. So if I keep going all the way around and I go on to the x-axis, y is 0 and x is equal to r, right? And I know it's in that side, in the negative side of x, because it says cosine theta is -1. That means theta is 180 degrees. In these special cases where it's 1 or -1 or something like that, you typically don't need to do the theta related thing, and there's only one answer. Otherwise, there's often 2 answers. Okay, we're not going to have time to do all 4, but maybe we'll do one of these. Use special triangles to determine the exact value of each of the following. So I'm going to do a little sketch of this guy. 225 degrees, remember? We know that's in the third quadrant. So 225 is my angle all the way around. But then what is my related angle? 225, yep. Yeah, so then if you rearrange, it'd be like 225 minus 180. And what does that give me? 45, right? So I might normally show some of that work, but theta, I guess we'll do it. 225 theta related is 225 minus 180, which is 45 degrees. Which special triangle is that? It's the isosceles one, right? So then I think about that, and I think tan is not the hypotenuse. So it's like 1 over 1 or root 2 over root 2 or whatever. So it's 1. Okay? So then I write this. The tan of 225 equals, and cast tells me that tangent is positive in that quadrant. So it's equal to positive 1. So that's that kind you could just put into your calculator. Like there are ways, and calculators are pretty good these days. They can give you fraction answers. So, you can kind of cheat, but you would need to, in grade 11 when you're doing this, you need to show your work.
Okay, we're going to slow this down a bit, take a look at a few more examples, talk a little bit more about graphing. Cosine of 210. So this guy is also in the third quadrant. Got to think about all kinds of different things here. Cast rule, what quadrants it's in, what the related angle is in. If this is 180 and this is 210, and theta related is 30 degrees. That's the triangle that we're interested in, right? That guy there. And then we want to think about the special triangle that goes with this. So 1, 2, root 3. This is the triangle that we're going to be using, and this is the 30-degree angle. So you could redraw this line down, or you can just think about the angle at the top. And cosine is adjacent over hypotenuse, so that is root 3 over 2. But cosine is negative, because tangent is the one that's positive in this quadrant. Cosine is negative, so this is equal to negative root 3 over 2. Okay, cosecant of 405. So this is an interesting one. This is one where I start here, go all the way around 360 plus another 45 degrees. So my related angle is 45. And I'm in the first quadrant, so it doesn't matter that I rotated around one full rotation plus a little bit more. In the end, it matters that I ended in the first quadrant, so that's what we're worried about. And cosecant is sine, but they're all positive in quadrant 1. So I'm looking for 1 over the sine of 45 degrees. And the sine is 1, 1, and root 2. And both of these are 45 degrees, but opposite over adjacent is 1 over root 2. So the inverse of that, or sorry, not the inverse, the reciprocal of that 1 over root 2 is root 2. So done. Positive root 2 is the cosecant of 405. Okay. And then this last question, cotangent of negative 120. So what is negative 120? Well, it means I went negative this direction, 90, plus another 30, which means I would have 60 left, right? So my, like this should probably have brackets around it to make it a bit more clear. So my theta related is 60 degrees, and it is in the cast third quadrant where tangent is positive. So this is, but it's one, but cotangent, tangent, so it's 1 over tangent, okay? And it's 60 degrees, so I'm looking at this same special triangle here. And where is my 60 degree angle? It's here. Tangent is opposite over adjacent, so that's root 3 over 1. And so the reciprocal of that is 1 over root 3. And it's positive. Whoops. So cotangent of negative 120 is positive 1 over root 3. We don't usually leave. This is like a standard, it's kind of like a lowest terms thing or an exact value thing in terms of reducing things and writing things properly. We don't leave radicals in denominators. So we call this rationalizing the denominator. And I multiply by root 3 over root 3. And this ends up as root, whoops. Uh-oh, what happened? This ends up as root 3 over 3 is the answer for that question. Okay, so if we want to think about sine and cosine, so this is, on this side we have sine. Y equals sine of theta, or sine x in this case. So here's the 5 key questions. The 0 line is y equals 0. The amplitude is 1, which makes the max 1 and the min negative 1. It starts obviously at 0. It has a period of 360, which means it stops at 360. And it's the same for cosine. It's just we notice that sine starts on the 0 line, goes up to the maximum, that's 1, then passes back through the 0 line, touches the minimum value, and ends on the 0 line. And if I think about the period of 360, I've broken it into 4 equal parts, 1, 2, 3, 4. And each of these parts is 3 squares long. That just has to do with how I set up the x scale, how many squares I'm counting by. It doesn't have to be 3 squares, but it's often kind of works out that way, or maybe 2 squares, or maybe 4 squares, something like that. Okay, and so then cosine starts at the maximum, passes through the 0 line, third point, so point number 1, point number 2, point number 3 is at the minimum, point number 4 is on the 0 line, point number 5 is at the maximum. So this one is y equals cosine of x. And then we can answer these 5 key questions looking at the transformations and use them to come up with our x scale and think about the transformations and think about where these 5 points are moved to. And so here's the example that we did in class where you can see that happening.
So how do we use that to graph? I don't know how you did it last year, but I do it with a method of 5 key questions. Anybody heard of anything like that before? You probably do it a similar way, but this is a really nice way of organizing it. So I would suggest you start. And so this is how I do it. Question number 1 is the 0 line. So the 0 line comes from the vertical shift, because it starts at 0 and it either goes up by the vertical shift or down. So in this case, it's y equals negative 2. Question number 2, I'm thinking about amplitude and max and min. So what is the amplitude? That's equal to the vertical stretch compression. The parent function amplitude is 1, so I multiply by 3. So 1 times 3 is 3, so the amplitude is 3. And the max occurs at the 0 line plus 3, which is 1. And the min occurs at the 0 line minus 3, which is negative 5. So I'm getting all these key points. So I have all these reference points, and then I can go ahead and draw my curve through it. Question number 3 is, where do I start? That's the phase shift. Both of them start when x is 0. But in this case, it's got a plus 30 degrees, so that's a phase shift. We don't call it a horizontal shift. We call it a phase shift, right? Because that's just because it's a repeating function, right? But we call it a phase shift. So I start at negative 30 degrees. Question 4 is, what is the period? And the period is 360 divided by k, and k is the horizontal stretch compression. So in this case, it's 360 divided by 2, which is 180. A k value of 2 has horizontally compressed my graph. Instead of having a period of 360, it has a period of 180, but it starts at negative 30. So the stop, where does it stop? If I'm graphing one cycle of this, it stops at the start plus the period, which is 150. I have to do a little bit more work. This should almost be like a 8-key question method. I don't know why we always call it 5, but anyway. So maybe you want to just watch. I'm going to figure out where my critical points should be and what my x scale should be. So I'm going to take my period and divide by 4. You always divide it by 4. So 180 divided by 4 is 45. And then what I'm going to do is find the x scale. I'm going to take 45 and I'm going to try dividing by 3. This is going to be the number of squares that I count over to draw it. So that works out to 15. And I ask, does that match where I start? Like, is 30 a multiple of 15? Because it either will be or it won't be. If it's not, I can't use 15 as a scale, because then my points will not be on the scale. But in this case, it works. So I give it a little check, and it works. And we're about to get buzzed here. So you might want to just watch. And I'm going to do this really rough. But I'm shifting down, so I'm going to kind of draw it like this. And I'm shifting over left, so I'm going to kind of draw it like this. And my x scale is 15, so I'm going to go 1, 2, 3 to negative 45. 1, 2, 3 to 45. 1, 2, 3 to 90. 1, 2, 3 to 135. 1, 2, 3 to 180. And that's more than my stop, so I'm done. Where's my 0 line? So let's see. I'll count 1, 2, 3. And then 1. So hold on. Sine starts on the 0 line. My 0 line is at negative 2. And it starts at my phase shift. And this is flipped. So I'm going to start by going down. So I count over 1, 2, 3. And I go down. Uh-oh, I go off the graph. 3, 4, 5. So it's right about here. 1, 2, 3. Shoot. That's good. And then 1, 2, 3, I'm back on the 0 line. 1, 2, 3, I'm at the maximum. 1, 2, 3, I'm back on the 0 line. And there's one phase, or one cycle of sine of that function. 5 key questions gives me all the information I need to find those critical points. And then it's easy to graph. Page 314, 1 to 7 has a bunch of questions like that where you just have to go, you're going over questions like that, reviewing it. This is really important because we're going to do something, we're going to start doing grade 12 stuff on Monday, and we add a whole level of complexity that can be kind of tricky. So if you're awesome at this and can do it in your sleep, all you have to worry about is the new stuff. If you're struggling with this, trying to relearn it, and trying to learn the new stuff, that's when it's really, really challenging, okay? And then page 315, A to J, has this neat little thinking activity about employing sine and cosine as an application. And if you don't get it done over the weekend, although you have the whole weekend, but if you didn't get it done for the weekend, that might be okay, but I would take a look at it at some point. It has to do with a Ferris wheel. And this Ferris wheel, where over time, as you can see, point C is going around on the Ferris wheel. It's graphing a trig function. Have an awesome weekend. Enjoy the show next period.